Hey guys, so welcome back to your next lesson of Catalyst concepts. In the previous session, we looked at something called series connections. All right, that is when you have just a single loop of connection and all your appliances or your loads are in the same loop. Right, today we'll look at another way of connecting our devices, what we call as a parallel connection. Okay. Now, this is a little obviously different from a series connection in the very fact that in series we said that there's going to be just a single loop for the current to flow. Over here, there won't be just a single path. There'll be multiple paths for the current to flow. So how do we go about doing that? So say assume that you have a battery system connected like this. Okay. And right, and this is generally how we have our series. Now say that I make this junction a junction wherein there is more than one path for the current to go. Okay, so let's say that over here I make another connection and put another load over here and then connect it back over here. All right, so this is now in this path. It can go either, the current can move either in this way or in this way. Okay, same way, let's say that I have one more like this. Okay, so basically at this point over here the conductor is splitting into three parts. Okay, one this, and one this, each of them having their own resistances or their loads, and they all come and connect back over here and continue to close the loop. Okay, so this is again a closed loop, it has to be. All right, so this is what I mean when I say that the current can have multiple paths to move in. Okay, so now how do I look at this? Say that there is a charge flowing through here. Okay, so the electrons are flowing from here. All right. Now, once the electrons flow here, what's going to happen is not all the electrons will go in just one path. Okay, since each of them has a different load attached to them, some amount of current of this I, part of it is going to go in that path. Okay, some of it will go in the second path and some of it will go in the third path. Okay, they are just going to split. Okay, that I splits down into three parts, not necessarily equal. They can be different values of current. They all split and pass through each conductor. Okay, so again I'll have I1 coming through here, I2 over here, I3 over here. When they come back and meet at this junction, you'll get the same current that was going in is coming out now. Okay, so now out of here I'm going to get back my original current I. Okay, so basically what I'm trying to say is in a parallel connection the current will be varied. Okay, if the current is varied like this, so that would mean the voltage is constant. Okay, so I'll say that for each of these load, if you check the voltage, you'll have the same voltage. Okay, so I'll say voltage is constant in a parallel circuit or parallel connection. All right, now say assume that these resistances are R1, R2, R3. Okay, so what that would mean is we know our basic formula V equals to IR, right? From here I can extrapolate or just change it up like this. I know V is constant. I just know that I and R are changing. So I'll say V equals to I1 R1. I also know that V equals to I1, I2, R2, and that V is also equals to I3 into R3. Okay, three different values for three different loads. Now, what I'm going to do here is, one more thing we know is that this current is split into three parts: I1, I2, and I3. Okay, and if I add up all the independent currents, I'll get my original total I current. So I know I equals to I1 plus I2 plus I3. I'm going to use this formula and these formulae to somehow make a connection. So if I look at this, V1 is V is I1 plus I1 R1, right? So if V equals to I1 R1, if I cross multiply, I can say that V divided by R1 is nothing but I1. Okay, I just moved the R on that side. Okay, similarly, I can say V by R2 is I2 and V by R3 is nothing but I3. Okay. And we already know that V equals to IR. So that would mean V equals to IR, then V by R equals to I. Right from that. Now, if I need to replace this connection with removing all these parallel resistors and just putting one equivalent resistor, how will I do it? Okay, so that is what I'm trying to find out over here. So instead of having a connection that looks like this, wherein there are three resistors, okay, instead of having this, I want to remove this part completely and just replace it with a single resistance that looks like that. Okay, this is what we call as equivalent resistance, right? Same thing that we looked at yesterday. So this is R1, R2, R3. I'll call this as R equivalent. So this over here, V by R is nothing but V by R equivalent. So I will say, let me use this formula over here. I equals to I1 plus I2 plus I3. Substitute the value in place of I. So I is nothing but V by R equivalent. So I'll say V divided by R equivalent equals to I1 is nothing but V by R1 plus V by R2 plus V by R3. Okay. So this way you have another equation over here. If I simplify this, I can put it like this. V by R equivalent equals to, let me take V. If you see, V is common for all of these. V into 1 by R1 plus 1 by R2 plus 1 by R3. Okay, so I can cancel V and V over here. So I'll say 1 by R equivalent equals to 1 by R1 plus 1 by R2, 1 by R2 plus 1 by R3, and so on. No matter how many resistances are there in parallel, you just need to reciprocate it and add the value. Okay. And this is the exact same way that we can simplify for any problem also. If you get a problem wherein you have different parallel resistances and they ask you to find equivalent resistance, this is the formula that you will use. Okay. Now let's take an example of one formula of one sum, what it can look like. Okay, say that your parallel resistances over here are given with values R1 equals to say 10 ohm, R2 equals to 20 ohm, R3 equals to 30 ohm, something like this. Okay, so what is the R equivalent? So 1 by R equivalent in that case would be 1 by 10 plus 1 by 20 plus 1 by 30. Okay, since they're fractions, you'll need to do the fraction mathematics over here. Now I know that the LCM for each of these will be 60. Okay, 32 is 60. And I know each of them can multiply by 60. So I'll take the LCM as 60. 10 6 is 60. So I can write as 6 by 60 over here. Plus 23 is 60 plus 3. 32 is 62. Okay. So this will come up as 11 divided by 60 ohms. You're not ohm yet. This is 1 by R equivalent. Okay, but I need to find R equivalent, not 1 by R equivalent. So what I will do, I need to do reciprocal for them, as simple as that. So you just invert these two. I do not have much space. So what I will do, let me just write it over here. Okay. R equivalent equals to 60 divided by 11. Okay, reciprocal them. Now, if I do 60 divided by 11, how much will I get? You will get 11 5s are 55.5. So 5, something like that. 5.5 ohms, roughly like that. Okay, so over here the answer should be again in ohm since it's resistance. All right, so this is all about parallel connections and how to find the equivalent resistance in a parallel circuit. That's it for today. If you have any questions, doubts, you can just drop them in the comments below. And I'll see you guys again back in the next class. Thank you.